Hello, everyone, and welcome to today's session, Strategies and Issues in Training Fairer ML Models. My name is Tom Alfetto from Clarifai's marketing team, and I'll be your moderator today. Before we get started, a few housekeeping mentions. All attendees will be muted, but we encourage you to ask questions, which you can do so by typing in the Q&A box or widget in the top right corner. We'll answer all questions after the session, which will last about 30 minutes. Today's session will be recorded and available after the event. I'd like to introduce today's speaker, Dr. Maya Gupta. Dr. Gupta is the CEO and co-founder of Didero, a startup company that drives high-quality content on the internet. Prior to Didero, Maya led the Glassbox machine learning R&D team at Google Research. She was also an associate professor of electrical engineering at the University of Washington, where she received the Presidential Early Career Award for Scientists and Engineers. Maya received her Ph.D. in electrical engineering from Stanford. Okay, a little background information on Clarifai before we get started. Clarifai is the leading independent provider of AI for unstructured image and video data. Its end-to-end computer vision and NLP platform covers the entire AI lifecycle. Clarifai has won numerous awards and is recognized by Forrester as a leader in computer vision platforms in line with companies such as Google and Microsoft. The company was founded in 2013 by our CEO, Matt Zeeler, Ph.D., after winning the top 5 places at ImageNet. Clarifai continues to grow with 80 employees at a headquarters in New York City and our offices in San Francisco, Washington, D.C., and Tallinn, Estonia. And without further ado, I'll turn the session over to Dr. Gupta. Maya?
Great. Well, thanks everyone for joining me. As we know, machine learning is making more and more decisions for people. And it's not just making decisions that affect how we think in terms of what books and movies we recommend, but it's starting to make important decisions about our finances and our prospects and our health and our wealth, from credit scores to insurance prices. So in some sense, this is great. I'm very excited that AI is able to make these important decisions because I think we can make much more accurate decisions. However, a lot of people are asking, who's really making the decisions when AI is making the decisions? And there's a lot of questions about trust and the quality of those decisions. Now, the short answer to this, you probably know, is that the training data is making those decisions, right? A good ML model reflects its training data. And one of the nice things about AI is that we can sort of crowdsource these decisions by getting a lot of different people involved in labeling and in creating this training data. However, as we're going to talk about today, there's a lot of questions in how you select the training data, how you understand the training data, how you represent it in terms of features, that's going to change how fair and accurate those decisions can be. And your responsibility in terms of crafting the decisions in the AI model goes beyond just the choice and curation of the training data. It really has to do with all of the aspects of an ML model. What features you choose, what training objective you're training the model to optimize for. We'll show how the type of model can affect things. And we'll talk a bit about how some constraints can be brought into play to make models fair. And just what launch metrics are you using to decide when and who to launch a model for. And today we're going to focus on the question of, when we make these models, are they fair? Now, the good news is I think just about everyone wants models to be fair. And some of the early work in AI suggested that if you had bad training data and people who were bad actors, that those could leak into the AI model. But the good news is that there's not really that many bad actors. And even when we have good people, though, we can sometimes end up with AI models that have some serious fairness problems. And a lot of that has to do with the complexity of the question, what does it mean to be fair? And I want to spend a little time emphasizing this because it's not something that we can simply say, oh, here's this one metric, we just need to optimize it. The whole notion of fairness lies at the intersection of a few different schools of thought. First of all, philosophical questions about what makes something fair. And then, as we'll see, there's psychological questions about what feels fair. And there's going to be society and contextual influences about what are the fairness issues that a society has to worry about. And then at the end of the day, a lot of this comes down to statistics. What can we measure? What is true? What is just anomalies? So I want to dig in for a second on that moral psychology issue, because it's part of what makes it so important in machine learning, is that fairness is something we really do feel. And dating back to 1740, David Hume already recognized that different people have what he sort of considered different tastes or sensitivities for different types of morality. To some people, it's really important. To some people, moral aspects are not that important. And then above and beyond that, the notion of what is fair differs. So some of the more recent work in moral psychology by Jonathan Haidt identifies 7 different dimensions of morality that people might care about. And there's no sense in which this is necessarily an inclusive list. But even in those 7 dimensions of morality, there's different notions of fairness. So some people worry a lot about the fairness of equal outcomes. Another type of fairness is whether we're giving everybody equal opportunity. But other moral dimensions include things like not doing people harm, community focus, purity, and some others. We're going to focus just on the fairness issues today. So if we look at these 2 different fairness dimensions, the equal outcome sort of says, look, if I'm making a classifier and that classifier is conferring benefits, like it's giving out free lunches, equal outcomes suggest that we'd like that classifier to give the same probability of free lunches for everyone or for every group of people. And we'll talk a bit more about these groups in a second. Whereas equal opportunity says, I want to make sure that people get free lunches, but only at the rate that they deserve them. So here, my probability that I'm giving out free lunches is conditioned on the training label being 1. So equal outcome sort of ignores the fact of whether people deserve them. Equal opportunity puts in that notion of deserving, but of course, there's a lot of questions about who made that training label, who decided who deserved what. So there's pros and cons to both of these. And one of the things we just want to focus on here is that different people will see different importances to different notions of fairness in different scenarios, and sometimes in the same scenario, and that may have very strong feelings about which one is right or wrong, depending. Okay, and to give you another sense of how complex fairness is, let's look at 2 ways that we might think about fairness in machine learning, and we'll see that they contrast. So the first sort of principle here is we might say, look, our ML model shouldn't distort reality, that the ML model should sort of reflect the data, and the data hopefully will reflect reality. So I'm showing sort of an example of this, which is a challenge that that companies like Google have to face when mapping, which is that you might be at the Stanford Library and you want a coffee shop. So you're looking for coffee near Stanford. Well, it's very easy to know where all the Starbucks and the Pete's coffees are in the world. The reality is those. And it might take a little bit more work, but it's sort of unfair to just go with the big chains and not necessarily surface the real coffee shops, local coffee shops that are also there. Okay, so that's one idea, that look, as ML engineers, we shouldn't be messing with anything. We should just, you know, try to reflect what's really going on in the real world. But on the other side of that, as a contrary opinion, is the contention that reality isn't fair, and that ML models are sort of our chance to implement justice, equality, and in some cases, the law. So we're kind of forced to think about both of these in the context of problems. And let's go and dig into some examples of how fairness problems arise. And as I said, certainly bad people and bad actors will train bad classifiers, but I think the real danger is that even good people, often trying hard and just going about their business, will also train bad classifiers. So we'll go through some examples of that. This, of course, is incomplete. We don't have time to talk about everything, but let's just give a flavor of how things can sort of go wrong. And our first example here will be the problem of data disparity. So let's say that we're trying to train an AI to predict who painted a picture. And so here's 2 test samples that we might have, and we might ask, you know, how accurate is our AI model going to be on these pictures? So some of you may have guessed who painted the picture on the left. That is, in fact, a Van Gogh. And it will probably be fairly easy to train an AI to do a good job of predicting Van Goghs. On the right, however, this forest is actually by Bokuyo, a Japanese painter from around the same time, but there's a lot less data that we can give the machine learning algorithm. He just didn't paint as many paintings. And so we're probably going to be a lot less accurate at identifying Bokuyos. And so the reality here is that if there's less data to learn from for some groups or some examples or some individuals, we may simply do a worse job for them. And that means that they're getting a less good AI model. Okay, so this, of course, can particularly make AI less accurate for minority groups or other people who are not represented as much. So that's certainly one challenge that we can deal with. And sometimes this is as easy as oversampling the data if the data exists. Here, we only have so many Bokuyo paintings, so we're just sort of stuck with the reality of this being a challenge. But even when we oversample, maybe we found as many examples of Bakuyo as Van Gogh, we may still just have the problem that some subgroups problems are harder to solve with AI. So just because you put in equal sampling or oversampling or equal effort or even more effort to make sure that some aspects are right, you won't necessarily get equal outcomes or equivalently good AI. So one example of that's sort of a pervasive example, is the difficulty of mapping in India. So if you're trying to build an AI and it's working on digital maps throughout the world, you'd ideally like to be able to map all countries equally well and not sort of have a classifier that's unfair or an AI system that's unfair to some countries. But if you look at Indian addresses, the Indian address system is a lot less formal than, say, America. And so you'll get addresses like this one for the Jain Lal Mandir, which just says it's opposite red fort. And that makes all of your AI harder than if you have like nice discrete numbers on a nice discrete grid. And so this also is a problem that we have to worry about, just making sure and identifying what groups are getting a worse experience because they're harder. Maybe we have to put more effort in if we want to make sure that they have the same quality AI experience as other groups. Our next challenge is about labeling. Take a second and decide if you're labeling, maybe with Clarifai's new labeling platform there, what would you label this image as? Okay, well, many of you might have said dolphin, but in fact, this is a porpoise. And to make matters worse, this porpoise was knocked out by a dolphin, so it's really sad to call him a dolphin. But this exemplifies sort of a general pattern, which is that we find that labelers are just less good at labeling minority classes or rare classes or just classes that they're not as familiar with. So that means that your ground truth data can just be corrupted by just labelers just not knowing enough. And so you always want the best experts that you can to label things. Otherwise, you'll just be less good at some classes or some problems because of this lack of knowledge. And so that makes a bit of a problem with saying, oh, I'm just going to reflect the training data, or I'm going to make sure that I satisfy the training data, because you got to keep in mind that your training data may have these kind of challenges. Okay, now we talked about different aspects of the ML modeling as being important to fairness. So we also need to worry about the expressibility and the feature selection. So let's say that we're making a college classifier. We might have trained a decision tree on these two features, GPA and SAT scores. But those might not be the best features for all groups to capture whether or not they're really college ready or whether they're the right student for this college. So we need to sort of reflect on whether we're really doing the best feature selection for all of our different subgroups. So that's one problem with this model. The other problem here is we might ask whether the model is flexible enough to really reward people fairly. So in this X, the red X at the top, this person's got a really high SAT score, but slightly lower GPA, and they're not going to be accepted according to this model. Whereas someone with a much lackluster SAT and just a little worse GPA is, because the model is just sort of set up to say you have to at least have this GPA and this SAT. And subjectively, other people might feel that a decision boundary more like this purple line that more trades off the SAT and GPA might be fair, but other people might not. And they both might have very strong opinions about whether or not the model is fair. So yeah. Okay, so those are some of the challenges and ways that models end up being unfair even when we don't mean to. What can we do about it? Well, the most important thing to do about it is just think about it. Just be conscious, be asking yourself, is my AI fair? Do I have any of these problems? Is there any other way in which my data is being corrupted or otherwise causing problems? And not just reflecting on it, but understanding your training data, being able to analyze it, understanding what groups are showing up in your training data and are important to your problem, particularly in a lot of video or image type problems. We need to worry about the darkness of people's skin color. That can affect how hard the problem is for them and may track or correlate strongly with subgroups that will feel that things are fair or unfair. And ideally, measure it. Figure out what you think you care about and make sure you're measuring it. As we all know, it's very hard to improve things if you're not measuring them. Lastly, there's quite a bit that we can do now to impose fairness during training. And so this is just sort of one sub aspect of the problem, but I'm going to spend the rest of the talk talking about it, in part because it's what we've worked on so much, and so I'm very familiar with it. But there's also some exciting things that we can do here. So what do I mean by that? Well, normally we take our training data, we throw it into this box, we cast a gradient descent, we train it, and we get out some ML. But what we'd like to be able to do is also have some policy goals. Those goals might be that we want them all to be equally accurate for certain groups or have equal recall or whatever our policy goals are. We'd like to be able to impose that upon the training and get not just an ML model, but ML that actually does what you want. One type of policy goal that we can handle pretty well are consequentialist or utilitarian policies. In math, machine learning math, these are called rate constraints. So I'm going to talk a little bit about these. One example is we might have this model that we're going to run across the world, and we might say, hey, we'd like that the accuracy in India is the same or roughly the same as the accuracy in the US. But accuracy might not be what we really care about. We might instead have a policy goal where we want to make sure that the recall in India is the same as the recall in the US. And this gets back to, well, which of these notions is appropriate for your model or your application to impose the right notion of fairness. And this is an equal opportunity metric. We might say, hey, people who deserve free lunches should get free lunches at the same rate in India and the US. All of these type of fairness policies or fairness goals can luckily be written with the same math. They can be written as these rates on the indicators of the classifier decisions. And I won't go into too much detail, but our group and other groups have developed game theoretic algorithms that you can use to train the model to respect these constraints. And there's quite a few papers about this, but I think this journal paper is a really good overview, both of the related work and of the state of the art by our group at Google that focuses on optimization with these sort of non-differentiable constraints. And it talks about how you apply that to fairness, recall, and also churn, which is model instability. So let's look again at what that lets you do. That lets you, usually when you train a model, like a classifier, you'll just say minimize the classification errors, and your stochastic gradient descent will go off and do that. But now we can add in these fairness policies. So we can say minimize your classification errors, but make that subject to making sure that the accuracy in India is no worse than 80% of the accuracy in the US. And here, notice that I'm no longer asking to be exactly equal, because in practical machine learning terms, it's very hard to say, I want these things to be equal. You've got to give yourself a little bit of slack. Maybe not 80%, but 90, 95% slack is going to be necessary to get it to work. And so you can do this with this open source library from Google called Tensor Flow Constraint Optimization. There's a nice blog post and some good demos about that showing you how to use that. And that you can use with any kind of empirical risk minimization model, DNNs, neural nets, linear models, etc. And as I said, there's very different notions of fairness that might be relevant. So one that I think is easy to talk about is this first one. I just want to make sure the classifier is equally accurate or roughly equally accurate for two different groups, such as India and the US. Equal benefits has to do with, well, if my classifier, again, is giving free lunches, what I really care about is that the free lunch rate is maybe the same in those groups. The equal opportunity says, well, I only care about that it's correct with respect to whether they really sort of deserved it by whatever notion of deserving makes sense. And then this last one we haven't talked about yet in this talk, which is no loss benefits. And here we're just saying, look, we're going to go launch a new model. But what we want to do is make sure that the positive rate of the classifier in India doesn't decrease. So we just want to make sure that no one's getting a worse situation with this new model. Maybe the new model is much more accurate in the US and we couldn't make it any more accurate in India, but we just want to make sure that we haven't hurt any of these subgroups at all. So again, these are all sorts of different fairness goals that might be relevant, and they can all be put together in the Tensor Flow Constraint Optimization, and you can train your model with these. And that looks beautiful, but there's a few caveats I want to go over. So let's say that we go off and we train our model and we say minimize classification errors and make sure the accuracy in India is no worse than 80% of the accuracy in the US. So let's look at what happens. Now with standard training, the accuracy in India maybe was 64%. This is just a toy problem. And maybe in the US it was 96%. Maybe it was much easier in the US. What happens when we add this fairness constraint to the training? We're going to get a new classifier that's going to obey this constraint. But what do we think is going to happen to these accuracy numbers? Well, a lot of people want to believe that adding this constraint is magically going to raise India to 80% of this 96% level of America. But in fact, we're not going to be that lucky. Almost certainly by imposing this extra constraint, we're going to end up with a model that is less accurate in the US and maybe probably more accurate in India. And you'll see this model now, the Indian model now has met that constraint, but we weren't able to get a free lunch here. We couldn't just say, oh, we're only just going to raise the accuracy in India. By adding this constraint, we ended up with less accuracy in some of the other countries. And so there's necessarily going to be some trade-offs there. So here, while we've now achieved this fairness metric of making the accuracy in the different groups more equal, we've lost some accuracy in the United States. And again, some people might feel that that was unfair itself. Some of the other algorithmic challenges with the sort of imposing these what we call consequentialist fairness is that if you have small groups, there's just not enough statistical significance, so it's hard to make sure that Alaskans are getting the same rate as the U.S. And sometimes the real problems are happening in intersectional groups where you have a few different characteristics. These again get very small, and the statistics get very hard to do. Another big issue is generalization. Just because you satisfy these constraints on the training data is not going to generalize to your test examples. There's pretty good evidence in terms of what happens if you have IID test, but if your test data is totally different, then there's not necessarily any good guarantees. And there's recently been some work on handling non-discrete groups, things like age or income. Okay, so that was a lot about sort of how do we impose fairness with respect to different groups. And we all belong to a lot of groups, but at the end of the day, we're also just individuals and not just categories. This is a picture here of my nephew Peter, who's like a quarter Indian and a quarter Dutch and half Minnesotan and all sorts of things, right? And a lot of people are like this. They overlap in a lot of groups. And so we want to ask, well, what else is there in terms of fairness that maybe is not just group-based? So there's a lot of different ethical principles, but many of them fit into these two threads or two possibilities. One is the consequentialist ethics. Is what actually happens when we run this model fair? Do we get equal accuracy for different groups? These are the ones we've been talking about so far. A different set of ethics is deontological ethics. These are what I like to call rule-based ethics. So let's look at some examples. And these are a little bit of silly toy examples. But in consequentialist ethics, you might argue that it's right to travel back in time and kill Hitler because you save a lot of lives. In deontological ethics, you probably wouldn't do this. You would say, look, it's just never right to murder. That's our rule. And in consequentialist ethics, if you're running an emergency room, you might say, hey, look, we should be triaging patients and looking to minimize the chance of death. That's our goal. That's what we're going to do, even if some people have to wait longer. Whereas in deontological ethics, you might use a more common rule of first come, first served. In an AI setting, what this often looks like on consequentialist ethics is that we want AI that works equally well with respect to some metric, we call whatever, for different groups. In deontological ethics, this is a bit newer. We don't have as much research on deontological ethics and AI. What we've done so far has come on my group at Google, looking at AI that doesn't penalize or reward unfairly. So being able to impose rules about how you should penalize or reward people. And just like we have an open source toolbox for consequentialist Tensor Flow constraint optimization, there is an open source toolbox that will let you impose deontological ethics called Tensor Flow Lattice. So let's look at a couple examples of deontological ethics in an ML setting. For this first one, we're going to look at some data about law school admissions and whether people pass the bar. So we have two features here, their undergraduate GPA and their LSAT score, and then the model's predicting whether they'll pass the bar. And on the left here, we have a DNN model. And this DNN model was trained on like 19,000 samples in 2 dimensions, so plenty of data. Okay, how do you guys like this model? Do people feel this is a good and fair model? Okay, I think this model is horribly unfair. And the reason is that there's a few places in this model, noted by these red arrows here, where if you increase that feature, you're getting a lower score out of the model. That's sort of a lower probability that you're going to pass the bar. And if we were using this to give scholarships or to do college admissions, this would basically be penalizing you in some cases for having a higher GPA or a higher LSAT score. So that seems really funky. And you might be like, but DNNs are awesome. How could they have done that? Well, they do some overfitting. And sometimes that overfitting is particularly bad in the sense that it violates these sort of basic fairness assumptions. So what happens here is that we have big data. We have 19,000 samples in 2 dimensions. We should be able to fit a great model. But the data is not uniformly spread out. And this is often the case. You have big data, but locally, you never have enough data. So here, we're down here in this part, we're seeing where we get the problems with this model. Okay, so this is sort of a violation of deontological ethics because you're not rewarding people for better GPA or LSAT. And what we can do is we can use a different toolbox called TF Lattice that also fits incredibly flexible, arbitrarily flexible models like DNNs, but allows you to force monotonicity so that you can impose policies such as a better GPA should never hurt your score and a better LSAT should never hurt your score. And so this is what the model looks like with TF lattice. And it's statistically, I think, indistinguishable on the test set. It might be a little better or a little worse. I'd have to look back at the paper. But statistically, it doesn't really change anything. But you end up with these monotonic models. And so now you have a fair model that never hurts people having a better GPA or a better LSAT. And that just means that, yeah, in any marginal line, along any slice, you're monotonic. Okay, that was a real data example. I'm going to do just a toy example, similar toy example, just to make sure we got the point through here. Let's just go to normal college admissions. We have SAT scores and GPA scores. We looked before at this decision tree classifier on the left, and now I've got another classifier on the right. This is a toy example, but this is what I might have gotten out of like K-nearest neighbors as a classifier. Which of these classifiers feels fairer? Well, again, I'm going to violate that the one on the right is violating a basic deontological ethic in that here, the red example has the same GPA as the green example, but a higher SAT score, and he's not getting accepted. Okay, so here we fit a great flexible model, but it overfit in a way that, basically broke some very basic concepts of deontological ethics. But again, just like before, we can impose monotonicity by using tools like TF lattice to impose those ethics. So just to go back to that other slide, we'd like to be able to take our noisy training data that's going to cause overfitting, decide what our policies are for fairness, whether they're deontological or consequentialist, translate that to math, impose it on the model, and hopefully end up with what we all consider fair ML. And in this case, for the deontological ethics, we've been showing how to impose monotonicity constraints on your model, such as GPA should only be a positive feature. We're going to look at one more example of that. This is another real data example from UCI, 24 examples. Again, we just have two features, whether people are going to default. So on the left is the data, and we're showing the error bars on the data. And it turns out it doesn't matter whether you're single or married. So really the only feature we're really looking at here is the number of months since you paid your bills and whether you'll default. Okay, so the data here is pretty tight for not very many months, but it gets really noisy for people who haven't paid their bills for many months, in part because there's fewer people out there. So again, sort of a data sparsity problem in the tail. So what happens when we train a basic standard model? Well, we end up again with this non-monotonicity problem that violates our basic notions of fairness, because we're giving a lower predicted default rate. So we're giving sort of a higher credit score, a higher goodness score to people who've taken longer to pay their bills, right? So that doesn't seem good. We're rewarding people to take longer to pay their bills. So that seems unfair. And again, we can use a toolbox like TF lattice to impose a monotonicity constraint on the number of months that you're overdue and get a model that that saturates it. It's flat here, but at least it's not doing the wrong thing. Okay, so just to go back and compare those. So we've talked about the consequentialist ethics that is sort of making the model work well or equally well for different groups, and some notions of deontological ethics where we say, look, you just shouldn't penalize GPA. It's a rule, and how you do that. And I'm pointing to a couple papers here for further reading. On the left, the Cotter et al. JMR 2019 paper, and on the right, Wang and Gupta AI Stats 2020. That said, there is a wonderfully huge literature on ML fairness. Anything that you're worried about, fair clustering, fair recommendations, fair representations, people have been thinking about and writing papers about, and I encourage you to find those on scholar.google and FatML, which is a fairness and transparency in machine learning website. Okay, so let's bring this all back. So we've talked about a lot of different stuff here, but really it comes down to figuring out what is the right policy and the right notions of fairness for your problems. And one of the challenges there is that what you think is the right policy or the right notions of fairness may or may not be what your customers or your users think is the problem or the policy. And so you may need to do some surveying and some iterative feedback, hopefully which does not include any PR disasters, to find out what people care about and what they're sensitive to. And then one of the biggest control mechanisms you have is defining your data, the training data selection, the features that you define, and making sure that those are useful, good features, and that your labeling is as accurate as you can for all people. And then as we've talked about, there's a number of choices in ML, how expressible your model is. You want to be expressive enough that it can really fit the truth and reflect what needs to be true, but you don't want it to be so expressive that it overfits and causes these sorts of problems that break these sort of deontological ethic rules. So balance of those two. In conclusion, though, I'm very excited about AI. This is really a huge opportunity, and it's a huge opportunity to make decisions that are cheaper, that are faster, that are more accurate, and honestly, that are fairer than human decision makers can make. Humans only have so much information, and they have a lifelong of experience that causes sometimes some subconscious biases, and they don't have the data to measure. When we do AI, we have the centralized data. So we can really start to measure and see what's going on and make sure that there's not holes, statistical holes that are causing unfairness for individuals or group. And because we can measure it, we can also work on improving it. And when we do improve it, we can get that out to all sorts of people very fast. So instead of waiting generations for norms to change, we can change our AI very quickly when we figure out that there's a problem. That said, as we've talked about today, there's a lot of different notions of fairness. It's a very complicated area that does lie at this intersection of philosophy and society and how people really feel in their gut. And so you've got to take it with a grain of salt and be humble, try to involve more stakeholders in the process as you try to figure out what's important in your model, your application. And at the end of the day, when we ask who's in control of AI, while many people are contributing their decisions and their training data, the model builders really have to take some responsibility for trying to make these models good and being aware of what your data is doing and what your model is doing and analyzing and hopefully continue to improve that. Okay, thank you very much.
Thank you, Maya. That was an excellent presentation. I personally learned a lot. Now let's take a look at the Q&A section here. So the first one, I think, is really more of a rhetorical question. It has to do with deontological ethics. It says, the classic problem, 10 people are tied to a track and a train, incoming train, and will run them over. One person is on a switch track, and if you pull a lever, we'll save the 10 and run over the one. You have control to let things happen. Second, given an AI-driven car, if someone runs across the road last minute in a snowstorm or heavy rain, where the AI only sees when it's too late. I think I said that correctly. So let me continue here. Okay. So the AI knows it could brake hard and save the pedestrian, but force would likely kill the driver. In both cases, she would let things happen and not intervene. What feature is important? The value of human life, which is fair to do in these situations? That's more rhetorical.
Yeah, I think we were touching on some of the standard textbook ethics questions here with the trolley problem, and of course the problem of how do we make sure that self-driving cars are appropriately safe for people, and the sort of issue of, well, should we be doing harm to people or not? Let's see if we can.
Good.
So I do want to emphasize that that morality and what is the right decision. I'm not here to tell you what exactly is the right decision in any certain case. I have my opinions and I express those through some examples. But these are really societal, philosophical questions that depend on what the people there think. And this is, again, why we need to get a lot of stakeholders to be part of this. And I want to bring back this diagram by Jonathan Haidt about the many mentions to the morality. People have noticed that Western educated people tend to be most focused on no harm, that it's not okay to hurt people. And that they sometimes are not as concerned about some of these other types of ethics, purity, following authority, loyalty. These are other values that some of the other cultures put more stock in, and they may be willing to, for example, go to war in order to and get killed as a soldier or something in order to defend some of these other ethics. So really complicated question, and for whatever your application is, make sure you're asking a lot of people who are involved what's important to them.
Thank you for that. The second question is, do you have a sense of fairness tools being used widely? Well, the sense of the fairness tools being used widely, I should say.
So be a little careful what I can say in terms of what's confidential at Google. I would say that there is a lot of interest and focus on these issues, and an increasing amount of tools and standard tools are being built particularly to do measurement and to help people slice their data and look for problems. But some of this is hard. I feel like all too often machine learning people pour their data in and they stir it around and something comes out the end. And if they don't like it, they just pour and stir some more, to quote an XKCD cartoon about this. Instead of really analyzing what's going on, what kind of people, what kind of examples are bearing the problems, and doing a little bit more analysis. So yes, there's a lot going on. People are starting to look at this, starting to measure, but I think we really need to do a lot more to understand what our models are doing.
Very good. I believe this is the last question. Maybe a little bit out of its realm, but are there disadvantages in using some of the open source tools such as TensorFlow that you had mentioned?
Sure. So originally, my group built a lot of tools in C++, and it took a little bit of time and effort for us to get excited about TensorFlow. Because there's always pros and cons to using software that someone else is building, right? When you build everything your own and custom, you get to control every aspect. On the other hand, when you use open source software, especially something that's a standardized platform like TensorFlow, you get all of the value of everybody else who's been contributing to it. And you also get all the documentation and all the help and all the expertise. And so it often does make it faster to develop models. That said, some of these open source libraries are slow. TensorFlow is getting faster, and with compilation, you can make them faster. But we recently published a paper on fast linear interpolation showing that we could be about 1,000 times faster by really doing really specific compiler optimizations for a certain kind of machine learning. So, there's going to be pros and cons with anything.
Okay, very good. I believe that's all the questions that we have for now. We'll give the audience another minute to see if there are any other questions. And no. So I will conclude today's session by thanking you. This was an excellent presentation. And I want to thank everyone for joining us today and let you know that the recording of this session will be available to you shortly, and you'll have access to this. So thank you very much, Maya, and everyone.
Organizing, really great. Thank you.
Okay.